I figured you could, and it took me like a half an hour to figure out what that problem was, like what was going on, that problem.
Let's get started, please.
Oh.
At the end of the hour last time, I just began the beginnings of a new topic, which concerns the Wigner Eckart Theorem and irreducible tensor operators. It's kind of a long story, and this is the most mathematical part of the whole course, so please bear with me. In any case, the context is that we have a unitary representation of rotations acting on a tensor space, which I call E. By using infinitesimal rotations, we can find the angular momentum operators. From them, we construct J squared and JZ, which commute. And from them, we construct the simultaneous eigenbasis, which we call the standard angular momentum basis, with an extra index in case of degeneracy. That's the basic setup for what happens when rotations act on ket spaces. Now, let's let psi be some ket, and let's let a rotation operator act on it. We can call this the old or the unrotated state. And let's call the new state psi prime, or call it the rotated or new state, call it psi prime. This is how the rotation operators act on ket vectors. Now, if A is an operator, let's say A stands for some operator, we like to define a rotated operator just like we have rotated states. Let's call the rotated operator A prime, and the question is what should be the definition of it? It's going to be something that depends on the old operator. What's the meaning of the rotated operator? Well, the definition is this, is that we're going to require, for the definition, that the expectation value of the rotated operator with respect to the rotated state should be equal to the expectation value of the unrotated operator with respect to the unrotated state. So the requirement is that if we sandwich psi prime around A prime, we ought to get the same thing as psi sandwiched around A. This is just a definition. In fact, it's a definition of A prime. It's a requirement we're going to impose. But it's a reasonable thing to do. Now, if we do this, the left-hand side, since psi is u of r times psi, the left-hand side becomes psi sandwiched around u dagger A prime u. And that has to equal the right side, which is psi sandwiched around A. And since psi is arbitrary, this is supposed to hold for all psi, we obtain that u dagger A prime u dagger A prime u is equal to A. And if we then solve this for A prime, we can fill in the question mark over here, which is that the rotated operator should be defined this way. It should be u of r dagger times A times u of r. And this will be our definition of rotated operators that we'll use. Okay. Now, it's customary in classical tensor and vector and tensor analysis to classify physical quantities by how they transform under coordinate transformations, such as a rotation as an example. For example, we talk about scalars, vectors, tensors, and things of that sort. And also in quantum mechanics, there's a similar classification scheme for operators. There's a classification as to how do they transform under rotations. And so I'd now like to tell you about that. In the first place, let's take the simplest example, which is that of a scalar operator. A scalar in classical tensor analysis is a quantity that's invariant under rotations. And we'll make the same definition here. We'll call an operator K a scalar if it's the same operator we get after we rotate it, like this. If we rotate the operator, the returns are back to the same operator. This should hold for all rotations R. And I forgot to mention this, but these are proper rotations only. We'll deal with improper rotations a little while down the line. So if the operator is invariant under all rotations, then we call it a scalar. It's a logical definition for a scalar operator. The most important scalar operators from a physical standpoint are Hamiltonians for isolated systems. They're invariant under rotations because the energy doesn't depend on the orientation of the system. And this has certain implications for the spectrum of the operator, the degeneracies, and so on, which we'll talk about a little bit, probably getting into next lecture. But in any case, this is the definition. Now, the next thing we'd like to define is a vector operator. Now, a vector operator in quantum mechanics really means, we say vector operator, but what it really means is a vector of operators, a collection of three operators, that have certain transformation properties under rotations. It's not sufficient just to have three operators. They've got to transform properly. I mean, for example, in hydrogen atom, you've got three operators, H, L squared, and LZ. These are certainly nice operators, and I can put them in a column like that. But that's not a vector operator because it doesn't transform as a vector. So in general, let's call a vector operator, we'll write it as V here like this, and you can think of it as having components Vx, Vy, and Vz. And the question now that we need to address is what should be the proper definition of a vector operator? Well, once again, let's refer to an unrotated state psi and a rotated state psi prime. If we take the expectation value of these three operators with respect to any state, of course what we get is a collection of three numbers. You can think of it as a classical ordinary vector and a classical C-number vector. Well, our requirement for the definition of a vector operator shall be that the expectation value, which is a vector of ordinary numbers, should transform as a vector of numbers does in ordinary tensor analysis. So the requirement is this. It is that if we take psi prime, sandwich it around V, the expectation value of the vector operator in the rotated state, this should be the rotated version of the expectation value of the vector operator in the unrotated state. In other words, expectation values transform as ordinary vectors in three-dimensional space. See, this is a vector of numbers here. Multiply that vector, think of it as a column 3 vector, multiplied by the matrix, gives us another column 3 vector. That should be the expectation value in the rotated state. Now again, this is just a definition. This is a definition of a vector operator. But to extract it and get a little more useful form for it, let's notice that since psi prime is u times psi, the left-hand side is the same thing as psi sandwiched around u dagger vu, like this. And since these two things on the two sides have to be equal and psi is arbitrary, this implies that u prime times the vector operator times u must be equal to the rotation matrix multiplied onto the original vector operator. Or, to put this into a slightly more convenient form, let's swap r and r inverse, and at the same time we swap u and u dagger. And if we do, then this becomes, I'll write it over here, this becomes u times the vector operator times u dagger is equal to r inverse multiplying on the vector operator. And this is a definition. This is a definition of the vector operator, just as this is the definition of the scalar operator. Now, in case this definition of the vector operator is not clear, what it means notationally, let me write it out in components. I'll just say or here. This is u. If you use u dagger to conjugate one of the components of the vector operator, this is the rotated version of that component, it turns into, r inverse is the same as r transpose, it turns into the sum on j of v sub j times rji. Rji is the components of r transpose. So this is an equivalent statement. The first one is just shorthand for the second statement there. Okay. So these are definitions of scalar and vector operators. Similarly, we can go on and define a tensor operator. A tensor operator is, let's call it Tij. It can be thought of as a matrix or a tensor of operators, 9 of them, I and j run over x, y, and z. And it has the property that if we rotate a component of the tensor operator by conjugating with u, that's the rotated operator over here, then we get a linear combination that looks like in which each index transforms in the same way as the single index does in the vector operator, basically by the matrix R transpose. And so what that means is this must be equal to a sum of k and l of tkl times rki times rlj, and that's the definition of a tensor operator. Tensor operator of rank 2. You can go on to define higher order tensor operators. The most important tensor operator for this course is going to be the quadrupole moment operator, electric quadrupole moment, which is important in nuclear physics, and we'll have something to say about that before too long. But in any case, this is the definition. Now, these definitions can be cast into somewhat different forms. Let me, first of all, take the scalar, which is the simplest case here. Let me erase this to make a little room. It's pretty obvious just from the definition that if I multiply by u of r on the other side, But this is equivalent to saying that k times u of r is equal to u of r times k. And so, in fact, it works both ways. And so this is another definition of the scalar operator. A scalar operator is one that commutes with all rotation operators, as you see. Or if the rotated operator is the same as the original operator, it means the same thing. Here's another equivalent version of a scalar operator. If this equation holds for all rotations, which it's supposed to here, it must hold in particular for infinitesimal rotations. So let's look and see what happens in the case of infinitesimal rotations. I'll do this over here. The u of r for infinitesimal rotations can be written this way: 1 minus I times theta times n hat dotted into j. And by the way, I'll set h bar equals 1 today, just the same writing. So that's the u of r factor here. And then I'll copy the k. And then for the u of r dagger, I just take the dagger of this, so this becomes 1 plus I, theta times n hat dotted into j. This is a rotation in axis angle form, and we're assuming the angle is small, so it's an infinitesimal rotation operator. And if this is a scalar, it has to equal k. Now, if we expand out the left-hand side, multiply it out, we first of all get k at lowest order in theta, and the next order term is I theta times the commutator of n hat dotted into j with the operator k. And there's a quadratic term in theta that I'll ignore because it's only lowest order, but it's important here. So if this has to equal k, then the k's obviously cancel, and it's obvious that the commutator must vanish. So it says that the commutator of k, our scalar operator, with n hat dot j is 0. This thing has to equal 0. But n hat is a unit vector. It's an arbitrary unit vector. If we choose it to be x hat, y hat, or z hat, the result is that the k commutes with all three components of j. And so we get the condition then that if k is a scalar operator, it commutes with all three components of the angular momentum. This is an alternative way of writing the definition of a scalar operator. Actually, all I've shown so far is that if k satisfies this equation, commutes with the rotation operators, then it commutes with angular momentum. But the converse is true too, because if k commutes with angular momentum, it commutes with any function of angular momentum, and that's just what the rotation operators are. So it works both ways. So these two things here, I'll just draw by a line here. These two things are actually equivalent. They're equivalent definitions of a scalar operator. So in particular, if you want to find out if your Hamiltonian is a scalar operator, you can compute the commutators with the angular momentum. That's one of the ways of doing it. It will imply if the answer is 0, it means that it commutes with all rotations. Now let me do a similar calculation for vector operators, which are here. Let's take a look at what happens with a vector operator if the rotation is infinitesimal. So it's a very similar story. I'll plug in, I'm looking at this equation right here, the u dagger sandwiched around b. So let's write u in infinitesimal form, 1 minus I theta n hat dotted into j. This is multiplying onto v. And then we have 1 plus I theta n hat dotted into j for the u dagger on the other side. And this should be equal to r inverse v. Well, I'll remind you, in infinitesimal rotation, an axis angle form has the form of identity plus theta times n hat dotted into these script j matrices, which, to remind you, I wrote them down here as a summary. Here they are, 1, 2, 3. That's the basis of any symmetric matrices in three-dimensional space. And so that's what this is. And if I take the inverse of this, then all I have to do is change that plus into a minus. And so this has got to be equal to identity minus theta times n hat dotted into j, multiplying our vector operator v, like this. Now again, I'll expand both sides out and multiply both sides out. The first term here is v. The next term is minus I theta times the commutator of n hat dotted into j, with our vector operator v. And on the right-hand side, you get v at lowest order. And then you get minus theta times n hat dot j multiplying onto v. But n hat dot j multiplying onto v is the same thing as n hat cross v. It's a cross product. So this becomes minus theta times n hat crossed into v. This is using the properties of the script j matrices. But again, the leading term cancels, and you can see the theta cancels as well. And I can bring the minus I over to the other side if I multiply both sides by I. And so we get n hat dotted into j, commutated with vector v, is equal to minus I times n hat cross v, if v is a vector operator by that definition. Now, allow me to transform this into a somewhat more useful form. Let's take the jth component of both sides, like this. So on the left-hand side, it becomes n hat dotted into j, and then v sub j, with the j component. And on the right-hand side, it's minus I, and then it's epsilon, let's call it epsilon jik times n I times n I v j, like this. And the n hat dot j can also be written as n I times ji. I'm using summation convention here. And this is a nice way of writing it because I've got the arbitrary unit vector n I on both sides, and since it's arbitrary, it can be canceled away. And what's left then is a commutator between ji and vj. Also, let's take this epsilon jik and write it as minus epsilon ijk by swapping the first two indices. And if we do this to summarize the results, it says that the ji with vj, the commutator, is equal to I times epsilon ijk times vk. And this is a condition which vector operators must satisfy. So, in other words, what I've shown is that this original definition of a vector operator implies these commutation relations with angular momenta, just like this definition of a scalar operator implies those commutation relations with angular momenta. We might say that there's two different versions of a definition. There's one that involves finite rotations, as you see here, and these commutation relations are effectively what happens when the rotation is infinitesimal. Likewise, for a vector operator, here it is for finite rotations, and here it is for infinitesimal rotations. It turns into commutation relations. By the way, this condition also implies that one, so these are actually equivalent definitions. And likewise, it's possible to express the definition of the tensor operator, which is way up at the top of the board, in terms of commutation relations with angular momenta, although I won't bother to write that out. All right. Now, more about vector operators. Let me first mention that there's at this point, there's a couple of simple theorems you can prove once you've got this definition of a vector operator. You can show, for example, that if you take two vector operators, A and B, and you form their dot product, the result is a scalar operator. This makes sense because it's just what you have in classical tensor analysis. Or if you take the cross product of them, you can show that that's, of two vector operators, you can show that that's also a vector operator. It follows the usual rules of a vector analysis. What about some examples of vector operators? To make a specific context, let's suppose we've got a particle moving in 3 dimensions, so the wave function is psi, the radius r, and let's suppose there's no spin, like this. Then in that case, we know the angular momentum L is equal to r cross p. Now, the position vector r is really a vector of operators with components x, y, and z. And you think that it really ought to be a vector operator by the official definition. Well, one way to check is to compute its commutation relations with the angular momentum. So in other words, you compute the commutators. The J here is a general notation for angular momenta, which in this context is L. And the V here, let's replace that by R. I'll write its components as x of I, or x of j here we want. So you can compute the commutator of Li with xj. And if you just work on the commutator, what you find is that it's I epsilon ijk times xk. It's a simple commutator to do. And so you see it does satisfy these commutation relations, and that shows that the position operator actually is a vector operator according to the official definition. Likewise, it's pretty easy to compute the commutators of the components of angular momentum with linear momentum. And if you do that, you find you get I epsilon ijk pk, showing that the linear momentum is also a vector operator, just as you would expect. Given those two facts, you can find some other facts right away. Since the dot product of two vector operators is a scalar, it means that the dot product of the position vector times itself, which is r squared, is a scalar. It's also very logical. But it means that the potential energy in the central force problem is a scalar operator. Likewise, the dot product of the momentum operator with itself is a scalar operator, and that means the kinetic energy in a central force problem is a scalar, and therefore the central force Hamiltonian is a scalar. I mean, these are pretty obvious conclusions, but this is in detail how you show it in all rigor. Now, again, using these theorems that I quoted here, that for example, the cross product of two vector operators is another vector operator. Once you've shown that the position r and the momentum p are vector operators, it follows that angular momentum is also. And so it must satisfy the same commutation relation with j replaced by L and now v replaced by L. So that's these commutation relations, Li Lj is equal to I epsilon I j k L k. And you recognize this as being just the standard commutation relations for angular momentum. In fact, this holds for any angular momentum on any system, not just orbital. And so you see, by this definition, you see the angular momentum operator is always a vector operator, according to this definition, or equivalently that would up here, this one up here. In fact, if we substitute v equals j for this equation right here, the definition of a vector operator, what we obtain is the adjoint equation for how angular momentum transforms under conjugation by rotations. So the adjoint formula is actually a statement that the angular momentum operator is a vector operator. It's another way of doing that. All right. Now, I'm going to change the subject slightly for the next topic, which is the spherical basis. So I want to tell you now about the spherical basis. The spherical basis is a basis of unit vectors in ordinary three-dimensional physical space, but it's not the same as the usual Cartesian basis. What I'm going to do first is just pull the definition out of the air with no motivation and show you what the properties are. Then I'll show you what it's good for, and then finally I'll give you some deeper insight into where it comes from and what it means. So first of all, let's talk about the Cartesian basis. Which is our usual basis. Let's call these unit vectors C1, C2, and C3, where C stands for Cartesian. And this is just the same thing as x hat, y hat, and z hat. Like that. The spherical basis is a different set of basis vectors. I'll use an E for them. One of them is E1, which has an overall minus sign, and then it's x hat plus iy hat over the square root of 2. Then there's an E hat 0, which is z hat. And then there's an E hat minus 1, which is x hat minus iy hat over the square root of 2 with an overall plus sign, like this. So this is just the definition. And we can denote these collectively by E sub q, where q takes on the value of 0 and plus and minus 1. You see that the index q looks sort of like a magnetic quantum number for something that's got angular momentum 1. Of course, with minus 1 and plus 1. Okay, like I say, this is just a definition pulled out of the air. However, let me show you some of the properties of the spherical basis vectors. One of them is that they're orthonormal. Well, before I get into that, it's obvious that spherical basis vectors are complex vectors, at least the 1 and minus 1 are. So this is a complex set of basis vectors for dealing with ordinary three-dimensional space, which is usually we think of as a real vector space. This means that if you have a vector that has real components with respect to the Cartesian basis, then it's going to have complex components with respect to the spherical basis. Seems strange, but it's useful. All right, so here's some of the properties of this basis. First of all, it's orthonormal in the following sense, that if we take EQ and dot it into EQ prime with a complex conjugate, you get a Kronecker delta QQ prime. That's just the orthonormality of complex vectors. You have to put a star in one of them. Here's another property. Let's suppose V is a vector, and let's define V sub q to be the component of V with respect to the spherical basis vector, so it's EQ dotted into V, like this. Then it turns out the vector V can be represented as a linear combination of the vectors EQ complex conjugated with coefficients which are b cubed. You can verify that directly just by plugging this in. But that's the same thing then as the sum on Q of E hat complex conjugated multiplied times E hat sub Q dotted into the original vector B. And since the original vector B here is arbitrary, both sides here, you can kind of cancel it from both sides. And you end up with actually a resolution of the identity. It looks like this. Identity is the sum on Q, it's E hat Q star times E hat Q. This is a resolution of the identity in ordinary three-dimensional space. This juxtaposition of two vectors next to each other like this is not a dot product, it's rather an outer product, or sometimes called a tensor product. This is like what you do in quantum mechanics when you write, Q outer product Q like this. It's the same idea. And if we allow both sides to act on some vector, here you get a dot product, E hat EQ dotted into B, and the right-hand side of the identity multiplying B is B itself. So it just reproduces this equation here. All right. So that's the properties of the spherical basis. Now, what is it good for? I'll show you an example where the spherical basis comes in. It turns out to be very handy. Let's consider radiated transitions in an atom such as a hydrogen-like atom or an alkali. I'll remind you that these are central force problems, and if we ignore the spin of the electron, then the wave function has the form of psi NLM of the position R, and this has the form of a radial wave function psi NL of radius R times the YLM of theta and phi. Now, let's suppose in the energies, I'll remind you, have the form E and L like this. In central force problems, the energies depend on these two quantum numbers. Hydrogen, pure hydrogen, is an exception because it doesn't depend on L. But as I pointed out, that's characteristic of the, very special of the Coulomb potential. And if you make any central force perturbation, small one even, to the Coulomb problem, you start to get an L dependence. So in any case, let's talk about two levels here. Let's say an upper level, which is called an N prime L prime, and a lower level, which we'll label by N and L, like this, and we're interested in radiated transitions going from one to the other. I'm calling these two levels, but actually they're not just single levels. There's multiple levels in there, because there's also a magnetic quantum number, M prime, up above, which means there's really two L prime plus 1 levels, indicated here by this line. And then down below, there's also a magnetic quantum number M, so there's two L plus 1 lower levels down below. The energy does not depend on M prime or M. So these lines that I've drawn here represent what they call manifolds of levels, or collections of levels, if they're degenerate. What you observe spectroscopically, if you're looking at a spectral line, is basically the frequency of the emitted photons. And that depends on the energy difference between the two levels. But that energy difference doesn't depend on the magnetic quantum number. So actually what you really get is a superposition of lines for all possible initial magnetic quantum numbers and all possible final magnetic quantum numbers. They all produce photons of the same frequency. And if you're interested in the intensity of the spectral line, you need to add all those various sublines together, because they'll all be the same frequency. Now, it's shown in the theory of emission of radiation that the intensity of a given spectral line, taking you from an initial state to a final state, is proportional to a square of the matrix element, in which you've got the initial and final states on the two sides, and the position operator in the middle. In the present case, the initial state is going to be N prime, L prime, M prime, and the final state is NLM, like this. Actually, what you're really doing, and the intensity is the square of this. This is a vector. This is a vector, of course, because it's an expectation value of vector operator. But you need to square it to get the intensity. In any case, these are the matrix elements that need to be computed. Now, by the way, what's really going on is that the position operator is multiplied by minus E, which is the charge of the electron, and this is the dipole. This is the dipole operator for the electron. This is the matrix element which is involved in dipole transitions. All right. Now, because of the common frequency for all the different transitions, we need to compute this matrix element for all possible values of m prime, all possible values of m, as well as the 3 components of the position vector. So let's say, for example, this were a 3D state, and this were a 2P state. This is an L equals 2, and this is an L equals 1. The number of matrix elements that you would get would be 3 for the position vector r, times 2L prime plus 1 for the possible m prime values, times 2L plus 1 for the possible final m values. And in particular, for 3D to 2P, this would be 3 times 5 times 3, which would be equal to 45. You'd have to calculate 45 matrix elements to find the transition from 3D to 2P. It looks like a lot of work. Most of the matrix elements vanish, as it turns out. In fact, the vanishing of matrix elements is governed by what's called selection rules. What we're driving for in this lecture, and probably on Wednesday also, is a more systematic theory of selection rules. So this is a simple example of what we're getting at. But there's still a lot of them that don't vanish. I think there's 9 of them that don't vanish. And so even if you calculate the ones that don't vanish, it's still a lot of work. All right. Now, so how can we simplify this? Well, in order to simplify this, let's begin by making some observations about the YLMs. So this is a little bit of a tangent now. We'll put this on hold and go on a tangent. Here are the 3 YLMs for the case L equals 1. Since you had a homework problem on it, I guess you've seen these already. If we multiply these 3 YLMs by the radius r, what we'll get is this. You get r times y11. That's equal to this normalization and sine minus the square root of 3 over 8 pi. And then r sine theta times e to the I5 is the same thing as x plus iy. Likewise, if you multiply r times y10, you get r cosine theta, which is z. So this is the square root of 3 over 4 pi times z. And if you take r times y1 minus 1, you get now the plus sign, square root of 3 over 8 pi, times x minus iy, like this. On the other hand, the spherical basis here, you see we define, here's the spherical basis up there, and here's the definition of the components of the spherical basis with some vector. If we take the, let's say, the plus 1 component of the position vector, it's going to be 1 over the square root of 2 with a minus sign of x plus iy. In other words, those components of the position vector with respect to the spherical basis are appearing here. And this can be summarized this way by saying the radius r times y1 cubed of theta and pi is equal to this normalization, which is the square root of 3 over 4 pi, times e hat sub cube dotted into the position vector r. This is what we might call r sub cube, the spherical basis component of the position vector r. All right. All right. So I have to, yeah, I've got it up here. So here's what we'd like to do. Let me take this back down. Instead of working on the Cartesian basis, x, y, and z of the position vector, let's replace this by the spherical basis, what we call rq, which is the same thing as e hat q dotted into the position vector r. In other words, I'll do it here. Let's look at this matrix element, n prime, l prime, m prime on the left, rq in the middle, and then n, l, m on the right. It's the same 45 matrix elements to do. But now, we can use this relation here that connects rq with the YLMs. In fact, rq becomes equal to, there's this normalization upside down, square root of 4 pi over 3, times the radius r times y1 cube of theta and phi. Like that. All right? And so, if I look at this matrix element and write it out as an integral, we bring it over here, has some room for it. There's first of all a radial part of the integral, 0 to infinity of r squared dr. Then there's the radial part of the eigenfunction on the left, that's r n prime l prime, of the radius r complex conjugated. There's the radial part of the eigenfunction on the right, which is r in L of r. Then there's the radial part of the operator in the middle, which is just a factor of r. That's the radial part of the integral. Now let's do the angular part. Well, first I'll pick up this constant factor here, square root 4 pi over 3. And then multiply this times the angular integral, which is the integral of the solid angles. So we get a y L prime m prime from the wave function on the left. This has to be complex conjugated. We get a y1q from the spherical components of the position operator in the middle. And then we get a YLM for the angular part of the wave function on the right. And the result is that this integral breaks into a radial part times an angular part. And all of the multiplicity that's occurring here of integrals that we need to do comes from the m and m prime and q. They're effectively three magnetic quantum numbers. And those three magnetic quantum numbers appear only in the angular part, not in the radial part. So our 45 matrix elements are really 45 angular matrix elements, times one single radial matrix element that only depends on the n's and the l's. As far as the angular integral is concerned, in last lecture I explained to you the 3YLN formula, which is used for doing integrals just like this. And the formula itself was reasonably complicated with constant factors, but a basic fact is that it becomes proportional to a Clebsch-Gordon coefficient, and it's this. It's L prime m prime scalar product with L1 mq, like this. The rest of it's stuff that doesn't depend on the magnetic quantum numbers. You can look up in your notes and see what the other factors are. But the point is that the dependence on the magnetic quantum numbers now appears here in this Clebsch-Gordon coefficient. Well, one thing to say right away is that there's a selection rule for the Clebsch-Gordon coefficient on the magnetic quantum numbers. This is equal to 0 unless m prime is equal to m plus q. In fact, this explains why most of the matrix elements that are 0 is they don't satisfy this condition. Now, this condition might not have been so obvious if we'd worked with the Cartesian components of the position vector up above. But by going to the spherical components, we get this selection rule. So right away, a huge number of matrix elements are 0. More than that is that if we really need to evaluate all of them, I think there's 9 that are left in this example that I'm talking about that are non-zero. If you really need to evaluate all of them, then the thing to do is just do the one single radial integral. There's nothing to do except just to do it here, the integral, by whatever means you can. But once you've done that, then by using the 3YLN formula, the rest of it becomes proportional to Clebsch-Gordon coefficients that you can look up, or you can calculate them. But in any case, this greatly simplifies the problem of finding those matrix elements required in the radiated transition. All right, so this is the second step of the spherical basis. First, I show you what the definition was, pulled out of the air. The second was to give you an idea of what it's good for. Now, let me turn to the third step, which is to show you the deeper significance of the spherical basis. I began this lecture reminding you of how what happens when we have rotations acting on a Ket space. You've got rotation operators, unitary rotation operators. They act on some Ket space E like this. From the unitary rotation operators, we get angular momentum operators. From those we construct J squared and JZ, which commute and have simultaneous eigenstates. And from them we construct the standard angular momentum basis, like this. Now, this general program here this general program can actually be applied to any vector space upon which the rotations act. It does not have to be a space of wave functions, that's to say a Ket space. There's actually interesting possibilities. Another possibility, instead of a Ket space, is this, is to replace E by ordinary physical space, ordinary three-dimensional space. So in ordinary three-dimensional space, we set up an inertial frame X, Y, and Z like this. And if we do this, then the points of three-dimensional space can be identified by their coordinates, and so they become real 3 vectors, R3, like this in mathematical notation. So we can say that E gets replaced by R3. Now, do the rotations act on ordinary physical space? Well, sure they do. They act by these classical rotation matrices. So in other words, U of R, in this general notation above, gets just replaced by R itself. These rotation matrices are orthogonal, and an orthogonal matrix is actually a special case of the unitary matrix. So this actually is a unitary representation of rotations. Yes, question?
So I just have a quick question. When you said that UR acts on the physical space, you just mean that by association, it's really the R that is acting on it. It's not really the U of R, is it?
Well, the general context is that you have a unitary representation of rotations acting on some vector space. Now, when it was a Ket space, we called those U of R because those were ordinary operators like in quantum mechanics.
Right.
But the space in question, the vector space, does not have to be a Ket space. So if it's going to be ordinary physical space, then E gets replaced by R3. And now the question is, do rotations act on R3 in a unitary manner? And they do indeed by the usual rotations. Those are in fact unitary. So in comparison to the notation we've been using, we'll replace script E by R3, and we'll replace U of R by capital R. All right. So if that's true, then what we ought to be able to do is, by looking at infinitesimal rotations, we ought to be able to get a Hermitian matrix, a vector of Hermitian matrices or operators that act on R3 that satisfy the angular momentum commutation relations. And then from them, we ought to be able to get a J squared and a JZ, and then from them, we ought to be able to get a standard angular momentum basis. I won't write it in the form of Kets because this is not a Ket space, but still it's going to be a basis, which is an eigenbasis of J squared and JZ. It's the same mathematical structure, but it's a different space. So the first step in doing this is to ask, what is the angular momentum, the Hermitian matrices? So to do that, we say, here's the definition of the angular momentum, is that if U of R, which in this case is the same thing as R, is equal to 1 minus I theta n hat dotted into J, this can be taken as the definition of J. This is the formula that applies when theta is small. However, on ordinary three-dimensional space, we know that an infinitesimal rotation can be written this way as identity times E plus theta times n hat dotted into our script J matrices like this. And the 1 here really means the same thing as identity. So these two are equivalent to one another if Roman block J is just equal to I times script J. And if you look at your script J matrices here, there's the basis of anti-symmetric matrices. If I multiply them by I, then they become the basis of Hermitian matrices. And in fact, it's just this. I'll write them out. You get Jx is equal to 0, 0, 0, 0, 0, minus I, 0, I, 0. You get Jy is equal to 0, 0, I, 0, 0, 0, minus I, 0, 0. And you get Jz is equal to 0 minus I, 0, I, 0, 0, and then 0, 0, 0, like that. And those are the 3 matrices. Now from them, we can construct J squared and Jz. We got Jz already. We can also construct J plus and minus, I might add. But let's look at J squared. If you take these 3 matrices and square them and add them up, it's an exercise for you. Here's what you find. You get 2's down the diagonal, and you get 0's on the off diagonal. In other words, the operator, or matrix J squared, is in fact just 2 times the identity. Now this means that every vector in ordinary three-dimensional physical space is automatically an eigenvector of J squared with an eigenvalue of 2. However, we know the eigenvalues of J squared have to have the form J times J plus 1, where J is an integer or a half integer. And if J times J plus 1 is equal to 2, it follows that J is equal to 1. And so ordinary three-dimensional physical space is a J equals 1 space in terms of how it transforms under rotations. fact, J equals 1 space has to be at least three-dimensional because the corresponding magnetic quantum number goes 0 to plus and minus 1. It has three values. In fact, this space is exactly three-dimensional. So, in fact, this physical space is actually a single irreducible subspace under rotations with an angular momentum value of 1. Now, this is associated, this is responsible for the fact that why, and we'll elaborate on this as we go, why vectors, ordinary vectors or vector operators, are oftentimes associated with an angular momentum quantum number of 1. Just to give you an example of this, the photon, which is associated as a particle, is associated with the vector potential of the electromagnetic field, is considered a vector operator, or a vector particle. And another way of saying that is that it's a spin 1 particle. So the fact that the photon has spin 1 is closely connected with the connection with the ordinary free vector potential and the fact that that's a vector operator. All right. In any case, so this three-dimensional space has J equals 1. And therefore, there should be a standard angular momentum basis, which is the simultaneous eigenbasis of J squared and Jz. Well, J squared is no problem. Every vector in the space is an eigenvector of J squared, so you only need to look at Jz. So if we just compute the eigenvector of Jz with eigenvalue plus 1, let's say, let's call this E hats of 1. And if you do, you find that within a phase factor, or we write it as a phase, because if you normalize it from the phase, it's all that's left, you find that it's equal to x hat plus iy hat over the square root of 2. In fact, it becomes, you see, the top vector of the spherical basis if you choose the phase to be minus 1. But then if you apply J minus to this, you apply lowering operators, what you get is the other three vectors. So the spherical basis is a standard angular momentum basis in this other space. In understanding this structure about how rotational operators act on vector spaces, it's a good idea to have a literal mind in terms of what the interpretation of the space is. It doesn't have to be a space of wave functions. I've just illustrated it could be ordinary physical space. It could also be a space of operators, which we'll talk about in a moment, if there's time, which there won't be, not today. It could also be a space of classical electric or magnetic fields. In other words, classical fields. And if you do this and you go through the decomposition into standard angular momentum bases, what you find is the multiple expansion. The multiple expansion of electric and magnetic fields is usually presented in courses on E&M as being power series expansion of a distant field in terms of a localized charge and current distribution. And it is indeed that. But it actually also is a decomposition of the electric and or magnetic field into its different angular momentum components. It's another way of doing the same thing. So for this reasons, as I say, it's helpful to have an open mind about the interpretation of that space E. All right. Now, I hope I have time to do this because there's one more thing I want to say about this spherical basis, let me do it here, which has to do with the transformation properties under rotations. If we go back to the case of a Ket space, and we take a standard angular momentum basis vector Jm like this, I'll assume there's no gamma needed. Let's take a look at what happens if we rotate one of these vectors, basis vectors, apply rotation to it. We actually went through this in the case of the YLMs just a couple of lectures ago, but I'll do it again. We can work this out by inserting a resolution of the identity right before the U. So we write this as the sum on M of Jm prime outer product, and then just copy the rest, U of R, Jm. And the result of this is this becomes the sum on M of the basis vector Jm prime. And then what's left over is a D matrix Dj M prime M of the corresponding rotation. So if you rotate one of these basis vectors, you get a linear combination of the basis vectors with the same J but other values of M with expansion coefficients, which are the components of the D matrix. Now, by an exactly analogous line of reasoning with just different notation, if we take a rotation and apply it to one of the basis vectors of the spherical basis, the answer can be written as a linear combination. Let's say some Q prime, V hat Q prime, vectors of the spherical basis with expansion coefficients, which are just the D matrices. In this case, it's D1, J equals 1, and it's Q prime Q of R. The derivation is just the same. Just insert a resolution of the identity. This, however, has an interesting consequence. If I take this equation and multiply by Q by D prime Q complex conjugated on the left-hand side, take a dot product, in other words, it will pick out one term of the sum on the right-hand side. And if let me write this dot product this way, it's B hat Q prime complex conjugated, comma, RDQ. I'll use a kind of a rounding parentheses notation for a dot product, but R act on EQ and think the dot product is Q prime star. Then on the right-hand side, we pick out the one term, and it becomes D1 Q prime Q of the rotation matrix R. And this is an interesting result because it shows you that for the case J equals 1, the D matrix is actually the same thing as the classical rotation, but it's expressed in terms of the spherical basis instead of the Cartesian basis. To emphasize this more, if I use Cartesian vectors over here, then what you get is the immutable components of the classical rotation matrix. So these two matrices, D1 and R, our familiar rotation matrices, are just related to one another by change of basis. That's all it is, going from Cartesian to spherical. This is all leading up to the Wigner-Eckart theorem, which is used in many applications in quantum mechanics. It's especially useful for analyzing matrix elements or finding out very quickly without doing any work when the matrix elements vanish. Those are the selection rules. I gave a brief example already with this. It's been erased now, this radiated transition in hydrogen-like atoms. It can also be used to greatly reduce the amount of labor that's involved in actually calculating those matrix elements if you have to end up getting numbers. And so, with any luck, on Wednesday's lecture, we'll cover the Wigner-Eckart theorem.